Blessings, everyone, and I hope everybody is doing great today. Now, today we're looking at our first latent heat question. The question reads: a styrofoam box contains 1.8 kg of water at 0 degrees Celsius. An insulated hose was used to deliver 0.3 kg of steam at 100 degrees Celsius into the water in the styrofoam. Assuming no heat was lost, what is the temperature of the water after the steam passed through it? Now, before we can do the calculations, there are certain things we need to consider or to make some assumptions. Now, the first thing I want you to note is that heat loss is equal to heat gain. Now, based on the nature of the question, we can make this assumption that the heat lost by steam is equal to heat gained by water. The reason for this is because the steam is at a higher temperature and water is at a lower temperature. So it's therefore important for us to note as well that warmer objects will lose heat to colder objects. All right, before we move on, let's quickly remind you about a few values. And these values are very important. You may need to use them or you may not need to use them. But the first value to note is the specific heat capacity of water, which is given as 4,200 joules per kilogram per degree Celsius. The second value is the latent heat of fusion. It is given as 33,400 joules per kg. Now, what is very important about the latent heat of fusion, and this is what you need to note, is that once you talk about fusion, you're talking about change from liquid to solid or from solid to liquid without any change in temperature. The next value to look at is the latent heat of vaporization. It is given as 2,260,000 joules per kg. When do we apply latent heat of fusion? Is when we're moving from liquid into the gaseous state or from the gaseous state into the liquid state. All right? So these three values of water, they are very important for us to apply to this question. Again, we may use them, we may not use them. Before I move on, I also wanted to note that the value of latent heat of fusion and vaporization may vary slightly based on the question given to you or the situation that you're answering the question under. All right, so please observe these values within your question and apply them accordingly. All right, so don't be alarmed if they're a little bit different. Now, the first thing I want to do here is to break down the question in terms of what was given. All right, so what we're going to look at now is the values given for steam, and the mass for steam is 0.3 kg. The temperature for steam was given as 100 degrees Celsius. The mass for water is 1.8 kg, and the temperature for water is 0 degrees Celsius. Now, to understand the concept of heat loss, heat gain, what you also need to note is how heat was lost and how heat was gained, respectively. All right, so let's look at steam first. Now, first we have steam at 100 degrees Celsius, right? Now, consider this, the steam passing through water at 0 degrees Celsius. What will happen here? The steam will lose heat. So if steam is losing heat, then the steam will condense. Now, just as steam condenses, just at that point where the steam is condensing, the temperature will not change. However, there will be a change in state. So therefore, we will have water at 100 degrees Celsius. And further cooling the water at 100 degrees Celsius, what will happen is that the water will move to an unknown temperature. We do not know the temperature because it was not given in the question. But we know if we further cool 100 degrees Celsius, it will go to a lower temperature that we don't know. Now, let's look at water that gaining heat. Now, what we know is that water was at 0 degrees Celsius. It will gain heat from the steam, so therefore it will move to a higher temperature. At this point, we do not know what that temperature is. But all we know, it will move up to a higher temperature. In fact, that is the temperature that they want us to calculate. Now, let's break this down a little bit now. Now, look at the concept here. We notice we have steam, which is gas, into liquid. So the concept to apply right here, steam to liquid, we're going to apply our latent heat of vaporization. Now, the energy to move from water at 100 degrees Celsius to the unknown temperature, which is lower than 100 degrees Celsius, it will be a change in temperature. Therefore, we can apply our specific heat capacity principle. Now, let's jump over to water. What is at 0 degrees Celsius? It will increase to a new temperature that we don't know, but what we know, the temperature will change. So therefore, we can also apply our specific heat capacity concept at this point. Now, once we have that, we can determine our formulas now. So the formula for the latent heat of vaporization will be given as the mass multiplied by the value for latent heat of vaporization of water or steam. Now, here, the specific heat capacity is given as the mass multiplied by the specific heat capacity multiplied by the change of temperature. Now, why we have an addition right here? Because this is saying the total energy moving from steam at 100 degrees Celsius to water at the unknown temperature. So we have a total energy on this side. So we have two different energy involved right here. Now, going over to the water side, we only have one temperature to deal, one energy to deal with, in fact, and this is given as the mass times C times change of temperature. All right, now once we establish this, we can go up now and calculate our values. So we're going to apply some values here now. So let's put our mass and let's put our value for latent heat of vaporization of steam. So right here going to be 0.3 multiplied by 2,260,000. And we're going to add that to our next energy right here. So the energy right here is given as MC, change in temperature. All right, so we have our mass, we have our specific heat capacity of water, which is 4,200. But we do not know our change in temperature. So we're going to put this back right here. Now, all of this now is equal to the heat gained by the water on this side. Again, we know the mass, we know the specific heat capacity of water, but we do not know our change in temperature. Now, what we can do now is go further and work out these that we know, which is 0.3 multiplied by that, which would give us 678,000. If we multiply 0.3 by 4,200, we should get here 1,260. And we're going to put back our change in temperature. But to put back our change in temperature, what we know is that at this point, it will move from 100 degrees Celsius to that unknown temperature, which is lower, because if you're losing heat, the temperature must what? Drops. All right, so we're going to say 100 minus that unknown temperature, okay? Let's go over to the water side now, and this is going to be 1.8 multiplied by 4,200, which gives us 7,560. Now let's work out the change of temperature right here as well. What we know so far that it was at 0 degrees Celsius, it will go to a higher temperature. So what we're going to have here is a higher temperature that we don't know minus 0 degrees Celsius. Now what we can do now is to further do some additional calculations. And so what we can do is to expand the brackets. So we're going to expand the bracket. So first, let us think about here. We're going to multiply this by this. So if we take this down, which is this going to be unchanged. So we're going to multiply here by here now. And so let's do that real quick. So 1,260 multiplied by 100 will give us 126,000. And then we're going to multiply the 1,260 by the unknown temperature as well. So let's do that real quickly. What we have here is 1,260 unknown temperature. Let's go over this side and do the same thing by expanding the bracket. And so we're going to have our 7,560 multiplied by this unknown temperature minus 0. So we could just drop the 0 off and just multiply that. And so we have this. Now the next thing to do is to put the like terms together. So let's work out the like terms. Now we're going to put back our 678,000. All right, we can add it to our 126,000 because they are like terms. All right, so let's quickly add that. Now, what you can do now is to put the like terms over to the other side. So we're going to have our 7,560 unknown temperature. And we're going to move over the 1,260 to the other side. Remember, it was a minus right here. So we're going to have to do an addition to bring it over. All right, so that's what we have now as a simpler equation. Okay, so let's add these together and then we add these together. So adding these together, what we get here is 804,000. If we had these two values together, what we'll get here is 8,820 unknown temperature. Now we could solve now for the unknown temperature right here by making it be the subject of the formula. And so we'll have 804,000 divided by 8,820. And what we'll get as a result is 91.16 degrees Celsius. All right, so this is our temperature of the water when the steam actually passed through it. All right, so we're at the end of it, and I hope this was really easy for you and quite organized for you to understand. All right, so at this time, I'm going to tell you that, hey, I truly appreciate you watching this lesson. And I want to tell you that sometimes we lose something precious in order to gain something priceless. So don't sweat the small things that you may lose along the way. Think about the bigger things that you may gain. At this time, be safe, be blessed. See you soon.